Hey, hello. Thanks for attending. We're going to talk about, indeed, about this KubeVirt project I work with, and specifically how our experience with using Golang in our project. So it's going to be a whirlwind tour, pretty high level. So, a few words about myself. I'm a software engineer. I work for Red Hat from few years. I'm involved in this project, which brings together Kubernetes and the virtualization stack. So my daily job involves Golang, which I'm very interested in learning more, by the way. So the outline of the talk, we will review the KubeVirt project. So we'll have a very, very quick recap about containers and virtual machines, similarities, differences. Now we'll get to the real business, which is our experience with Golang in this KubeVirt project, and we will deeper dive in a couple of stories which highlight some key features. So what is this KubeVirt about? We want to bring together virtual machines and containers. I told you already. So what's a virtual machine? Very quick recap. A virtual machine is a program which allows us to virtualize a complete computer system. So it allows to run another operating system on top of our operating system, and we present virtualized hardware to our operating system, to the guest operating system. So we can configure how this virtual hardware could look like, and we will also can leverage some acceleration features of the hardware, for example, recent Intel AMD CPUs, or specialized hardware like network cards. An important topic is the hypervisor, which is the manager which allows virtual machine to run. An hypervisor could replace an operating system, or could be a component of operating system. For example, in Linux, we have the KVM subsystem, which is an hypervisor, and also allows us to access the acceleration features of the CPUs. On the other hand, the component which virtualizes the hardware proper is called QEMU. Well, there are many, but one of the biggest and most important is QEMU, which indeed presents the virtualized hardware to the guest operating system. Here's a picture which presents how the software components are stacked out. So we have hardware, we have the operating system or the hypervisor. In our case, we have the operating system with the hypervisor module KVM. Hopefully it's visible. And on top of that, we have our regular programs and our virtual machine, which is the bigger box, which is on one end is another program. On the other end, it pretends to be another hardware, another box altogether. So we have the virtual hardware, the guest operating system, and eventually the guest applications running inside. On the other hand, containers. This is the other half of what KubeVirt is about. Containers are a big topic in the last few years, but containers are actually, for Linux, are actually an aggregation of features of the Linux kernel. So we have a lot of layers and a lot of components. We need to interact with each other to create this isolation and make the application running in the container pretend to be the only one of the system. Using those kind of confinement technologies, you can limit, for example, how much memory, how much CPU, how much I/O bandwidth our process have. But you need to actually make a lot of feature work together. So you most often want to have a manager or a container runtime, for example, Docker, Rocket, or a lot of others, less famous, to have all these feature works together to create a container. So here's a diagram which could help us to understand how containers are placed in the stack. We have just this new box, which is the container runtime, which is just an helper which allows us to put all those features together to limit the scope of our containerized application. I just said moments ago the containers do two halves of the picture, so are they side by side. So there are similarities and differences, but in the end, their similarities are probably more than the difference because you can think of your virtual machine like a regular process, which is ultimately is. So the big benefit of containers is that you can containerize your applications, so you have an easy way to pack them together and let it run on someone else's computer, or maybe even on a fleet of computers on the cloud. So you pack your application with all the dependencies, maybe resource files or whatever else is needed to run, and you ship it. And hopefully it will work the first try. But to run those containerized applications on a fleet of hosts, you may very likely need a management platform. Kubernetes is probably the most famous. So Kubernetes allows to run these your containers on a fleet, let them scale, you can monitor them, you can do everything you need and probably more. And here comes KubeVirt, which is an add-on you install in your Kubernetes or OpenShift cluster, and you get the capability to run virtual machines. KubeVirt is built on top of Kubernetes feature and brings with it the virtualization stack in a transparent way. You just gain a new Kubernetes type, which is a virtual machine and few others, and you run virtual machine containerized on your cluster side by side. Otherwise, you will need probably two control planes. The nice thing is that you now have just one control plane. Here is that how it could like if you take a look on a single host which run them both. You see that you have now a virtual machine layered on top of the container runtime because you have a virtual machine running inside a container. So this is basically it. This is what KubeVirt is about. Now KubeVirt is meant to be a part of the Kubernetes ecosystem, and it is. So it is the container and Kubernetes ecosystem is written mostly in Go, and indeed KubeVirt is written in Go. So on one end, write this project in Go is pretty much a forced adoption, because when you have such a rich ecosystem, you want to make use of it. On the other hand, this is not really an issue by any means, because Go is awesome, we know at GoLab. So now let's talk about which features of the language we particularly found interesting and helped us, or helped us a little less than we expected. So the usual suspect when we learn about Go is among the very first thing we know about Go is how awesome the compiler is, how fast it is, and how that impact us, or impact most of developers. Well, the compilation times are fast, so you have quite a fast turnaround time. Totally true, totally awesome. But we'll see that in a moment. Sometimes it's not really that shiny for other reasons. Another great thing we have is the tool. We had examples in other sessions today. I want just to mention how nice the Ginkgo and Gomega tools they are, and they plug so nicely in the existing infrastructure, and everything feels integrated. So I mentioned the static linking, which is a big thingy about Go as ecosystem, because one thing with when the tool chain is presented, it is presented like a big upside, because you have just one artifact you can ship and deploy, and this is indeed awesome. But when you have containerized application, you already have an easy way to ship your artifacts, and so far so good. But on the other end, depending on how container they are made, very quickly they are made with layers. So when you have your big artifact, I mean like hundreds of megs, then your layers become big. So again, you gain something, but you lose something, because you have bigger download times, and somehow the developer flow chokes a bit again. So this is not something that it is not solvable. There are indeed mitigation and way to circumvent this issue, but still this is something that gets in the way, and you have to deal with it. So this is pretty much what I just said. And yes, another really nice feature of the Go is the C interoperability. We have, not sure other session mentioned or deal with that, but still, we have this CGO module, which is totally great because you can just consume C libraries. And how that helped us, because the component of the virtualization stack are very big, mature projects, multi-millions lines of code big, and we wanted to use them from day zero. And we did, because using CGO, you can just consume those libraries and have easy access to client libraries. And so we are able to consume, for example, KubeVirt, which is the management layer built on top of QEMU from day zero. Another option is always to re-implement the client side in pure Go, and it is often possible, for example, when the server API is accessed across the network, so using network protocols. But having the possibility to consume the client libraries using very tested code was nice, and we enjoyed from day zero. Okay, this is somehow the easy part, and the part you face when you first read about the great features of Go. Now I would like to dive deeper in a couple of stories we had during the recent months, which are, I think, interesting. So, first story is about validating the configuration. So let's have a step back. Why we need to talk and to deal with that in the first place? Pods are relatively simple objects when you need to configure them. Pods are the basic building blocks of Kubernetes, if someone doesn't know. So when you configure your objects running on containers, you have relatively few knobs to tune. On the other hand, virtual machines do have a lot of configuration options, and this is actually a good thing, and you want to keep them. Problem is, some of those fields depend on each other. And by depend on each other, I mean they have values that are legal or illegal depend on other fields in the VM configuration area, or they become optimal or suboptimal depending on those other fields. Here is an example taken from a screenshot of a GUI, a graphical interface to manage virtual machine. This is actually Virtual Machine Manager. It's hard to convey how many options you have and you want to have, because you want to have a very fine control on how the virtual hardware look like and how the virtual hardware is mapped on the real hardware. Otherwise, you could not have optimal performance if you don't bake back a virtual device with a real device. Example, a virtual network card to a real network card. So you have those plenty of options, you want to keep them, but you want to preserve the Kubernetes look and feel, you want to somehow help your user, you don't want to overwhelm them, and you want to bridge the gap between this rich set of features and the relative simplicity of the containers. So we use templates. Templates are pretty much, like the name suggests, are the blueprints of objects with relatively few fields you can tune, and we present them to the user, for example, using a web user interface. So you have fewer fields to tune. Of course, you can have the access to the full range, but you can have a simplified view. However, we still have the problem of interacting fields. For example, again, you can expose a multi-queue network interface card, and you want, for example, to tune how many queues you have, so how many real concurrency you can have, your real parallelism you can have. But these fields, this value, for example, depend on how many virtual CPU you have. So you have interdependent fields. And those fields depend how they are expressed. They are expressed using JSON path notation. For example, you have, let's say, domain.virtual.cpu.count. It's not a real deal, but you get close enough to have an idea. So you want to express those relationships. But there is another but, because the data structure which represent a VM configuration is deeply nested, again, because how the configuration is made is deeply complex. So when you translate this to data structure, gets very, very complex and nested. And you can have default objects, so some objects could maybe not exist because they are, for example, expressed as pointers. Pointer is nil, that means this is a default. So when you take a JSON path from the root object to the end object, this path can be broken because a nil object could be in between. So how do you distinguish between a broken path and an illegal path? What's an illegal path? A path is a path to object that could not possibly exist. If the foobar device does not exist, it could not possibly exist in the tree of your object in your object tree. On the other hand, you maybe have the default device, so it is not yet there, but it is legal. The package we use to deal with that cannot make this distinguish, which is also pretty hard in the general case. So we use the reflect package to fully explore, dynamically explore the data structures representing our VM configuration, and dynamically create all the missing objects along the way and initialize them. So we get the nice benefit that we can now traverse this tree of objects, and if a path fully exists, then the path is legal. So the rule we have is okay, is great, is legal, and we get for free the zero object. Takeaway, this is actually pretty easy to do. It's less than 200 lines of code, and it's surprisingly easy. Sometimes the reflect package gets a bad reputation. It's hard to use. It turns out you've read a few lines about the documentation is not that hard. One may rightfully ask, why just not patch the upstream package, with something we are up to? Again, handling the general case, which they are rightfully focusing on, is not really that easy. Another story about monitoring. So we need to monitor VMs, how they behave, how much resources they consume, how they are doing, so how the virtual CPU are used, how the virtual NIC are used. Again, stop and pause. You already know that, because we said in the beginning, VMs are running inside the containers, and the container runtime like Kubernetes provides us all kind of metrics, but we want another set of metrics about what's happening inside the container, not just outside the container boundary. We need to access inside the container boundary. So we want to access the VM metrics, not just the container metrics. We have a very nice API provided by KubeVirt, which is again the management layer, if you're not aware, which we use, and it is pretty much a standard. So far so good, easy, why to bother at all? Unfortunately, we need to bother because the API we use could be blocking, and by blocking I mean not blocking in the IO sense. Blocking I mean that if something goes wrong, because for example I will get to that in a moment, but if the API could block for a long time, for a long time I mean minutes or maybe hours, if the VM is behaving badly. Okay, just to provide some context, this happens at all because virtual machines do use the shared storage. So the storage, the virtual disk, sorry, they are not backed by host local storage. We need to access the storage across the network because we want the virtual machine to be migratable, and to make them migratable, we need to have to access the storage from both sides of the migration. So this is what makes it possible. And again, why to bother in the first place? Because live migration is a key feature of VMs. We want the VMs to be alive and well, even if we need to move, for example, the host on which they were running in the first place in maintenance. In comparison to containers, VMs, the VM uptime is something we deeply care about. So, back to the real business. virtual machine, to monitor them, you have synchronous, possibly blocking API, and for blocking, I mean blocking for minutes or even hours. It is something that should not happen, but could happen, and we need to deal with that. We cannot just file an upstream bug and be done with it and just wait for the fix to happen, because these unfortunately have deeper design issue. This is actually a long-standing bug open. So how to deal with that? Again, we cannot just say, okay, it's not responding. We know nothing about metrics, because we need those metrics to do some important management operation, and we want to know what's happening. Otherwise, some key features like self-healing and self-scaling could be out of business too. So this is problem we solved before. We solved before because I worked in virtual machine management solution, and indeed this is a known issue, and we have solution to this problem. So let's quickly go through the possible solution. Of course, event loop comes to mind, but it is not really possible there because of the how the API looks like. So we need threads, long story short. One thread per VM is not really possible, doesn't really scale. So again, the most common solution is a thread pool, but managing those kind of issues with a thread pool gets hard really fast, because you cannot afford to have one misbehaving VM to block the entire thread pool. So you need to, for example, to deal with blocked threads in your thread pool, to replace blocked threads, to have deadlines, timeouts. It's not like rocket science, but it is hard to do properly and hard to tune. How Golang helps with that? We just throw Go routines at the problem, and they work. And it is simple, because Go routines are cheap, Go routines are fast to spawn, so instead of threads, they scale up really well. And instead of threads, you can just spawn a Go routine to run your monitoring. If it blocks, it blocks. You just need to do some minimal bookkeeping. And so far, so good. So really that good? No, because you still have to do some bookkeeping. For example, track unresponsive VMs, meaning if a monitoring Go routine doesn't respond quickly enough, you have to track it and be aware of that, because you don't want to throw Go routines at an impossible for the moment task to waste them. And you need, for example, to do some throttling. But why throttling? Because we need to conform to the Prometheus model. Prometheus is the standard solution to monitoring Kubernetes clusters. So, and Prometheus is a pool, a complete pool. You are supposed to extract fresh data from your Prometheus endpoint every time you are requested. So, long story short, you are supposed to spawn Go routines every time you get a request from Prometheus. So again, minimal bookkeeping, but much, much simpler, something like 1 order of magnitude simpler and safer. And this is pretty much it. So what's the takeaways I can give you? Well, the takeaways is that I will like to highlight 2 things. First thing is, again, do not fight the ecosystem. I mentioned before I was involved in a virtual machine management solution, which is KubeVirt, which is great, but and somehow I had the temptation, I must admit, to re-implement the old patterns in the new language, in the new ecosystem, in Kubernetes, in Go. We all knew probably we should not do that, but sometimes it creeps in. Do not do that. Try hard to reevaluate your design choices and the tool you are using, and conform to the ecosystem. It is much easier. Do not fight the stream. Do not swim against the stream. And the other thing I would like to highlight is that is related to this one, is that you have to reevaluate your design choices depending on the tools you have available, but this road goes in both directions, because you want to reevaluate your design choices to work best with the tool you have, but you can also pick the tool you have depending on the design choices, and vice versa. So it's a circle actually. The direction is again goes both ways. This is everything I have, so I give you some minutes back. Yes.
Are you leveraging like any CNI plugins that exist in Kubernetes to handle the networking on the VM side? If so, like, can I utilize things like network policies?
We totally do. We totally use CNI. And other than that, I'm not really that expert in that area, so I cannot unfortunately answer properly to the second part of your question. But yes, we do, and we are totally trying to conform as much as we can to the ecosystem. So if you want to have a look, somehow I forgot to mention that the website is kubevirt.io. Very simple, so you can start from there and get all the links you want. Yes, please.
You mentioned that you're using Seago instead of the network-based connectors.
Yes.
Were there any surprising learnings from using the Seago extensively, like go routine access?
In
You wish to have known beforehand?
question is if using Seago had some surprises or unpleasant or gotchas moments. Answer is, as far as I am aware, no. It worked the way we went for our use case. Another important things to know is that we consume the Seago, we use the Seago indirectly. So I'm not aware of, for example, intricacies or issues in the Go side. So because it's third party, it's the KubeVirt client libraries. So if they had an issue, I don't know exactly. But from our perspective, brilliantly. Any other question? Yes, please.
I understand that you make an patch upstream to check new problems with the configuration. Is there any like things like when it will be merged?
Sorry?
So this is about like a new configuration.
Mm-hmm.
Based on that.
Mm-hmm.
It's a problem when your object is not defined there.
Mm-hmm.
It gets new. Otherwise, so you make a patch probably CRD, right, to make evaluation.
Question was if we want to.
Will we merge a patch, your patch to upstream to Kubernetes?
Question is, yeah, sorry if I interrupted. Question is if we had, we want to send the patch upstream to work to fix the validation issue mentioned. We are trying to contribute back as much as we can to upstream first. Problem is that our use case is not well aligned to the use case we use this package for is not really well aligned to their use cases. So it's not a bug per se. It's not like a real issue. It's that it doesn't really fit well our use case. So we would like to contribute back, but having a solution which fixes for us, but solves the general case is still in the works. We would like to, but not there yet. Anything else? Yes.
Are there any restrictions about operating system? I'm guessing not.
Not at all. We want to run the
Windows,
we want to run the real virtualization stack everyone knows about, like QEMU and KVM, and is the same virtualization stack. It is used by other solutions, so unchanged. So everything runs in the virtualization, like in QEMU, for example, with KVM, will run on top of Kubernetes. No, some operating systems are more supported than others, but nothing is explicitly unsupported or discouraged to use. Yes, please. Question was if we support NUMA topology or if we allow something that it is not yet supported or exposed by Kubernetes. And yes, NUMA is a good example because we don't support yet because we still want to figure out how to do properly. So as well, this is what I'm aware. I'm not aware of recent, last week developments, but as far as I know, NUMA will be there, but not there yet. Anything else? Okay, I guess that's all. Thank you all for attending. Thank you.